So today we're going to talk about concavity in a bit more detail. The first derivative we've seen measures the slope of the curve at a particular point. The second derivative then measures the rate of change of the first derivative. So the rate of change of the slope. Well, that's what concavity is. So if you have a positive concavity, so let's just look at our parabola over there, our classic one, we know that's concave up, it has positive concavity. What it's saying is your slope is becoming more positive. So if we start on the left-hand side, we obviously have a very steep negative slope. But as we move from left to right, it's becoming more positive, until we get to the right-hand side, and we now have a very steep positive slope. So that's what a positive concavity means. That's the way it moves. And negative concavity, obviously, the other way around. If the second derivative is positive, then we know it's concave up because it's going from that negative slope through to a positive slope. If it's negative, then we know the curve will be concave down. Now what this means is we now have another way of classifying turning points. We don't necessarily have to draw the boxes up now, because we can just plug it into the second derivative and we know what the concavity is. And if we combine that information, okay, I know it's a stationary point and it's concave up, well, then it's got to be a minimum turning point. So I can save ourselves a bit of time. Of course, that leaves one other option, and that is if there's no concavity at all, and that's what we call a possible point of inflection. We'll talk more about points of inflection later. Okay. So now we're going to draw this cubic, but this time by looking at the second derivative. Well, before we can find the second derivative, we've got to find the first derivative. Differentiate a second time, we get 6x plus 10. All right. So really, if I'm looking at the concavity, I know it's a cubic, and classic cubics, we now have those two turning points. So really what I'm interested in is this going to start concave up, then go concave down, or is it the other way around? The interesting point to work out then is, well, when is it always positive? When is it concave up? I suppose I could have just as easily worked out when it's concave down, but I've chosen concave up. So I solved this simple little inequality. So I know that when x is negative 5 on 3, that's when it's going to change its concavity. So a very rough sketch then. Well, there's minus 5 on 3. So I know, well, on the left-hand side of that, it must be concave down, and on the right-hand side of that, it must be concave up. So as I say, a very rough sketch. But as I say, if we combine that information with stationary points, we can now find information about those stationary or turning points. Because, of course, all turning points are stationary points. So our first procedure is to find them. Second procedure, classify them. As I was just saying, if I know it's stationary and concave up, must be a minimum turning point. Concave down, must be a maximum turning point. Now, let's find our turning points. Again, we'll differentiate it once so we can locate the stationary points, but now we'll differentiate a second time so we can go and classify them. Remember your setting out. Explain what you're doing. So the first thing I'm saying, well, okay, first thing I want to do is go and work out where the stationary points are. So stationary points, I know they're going to occur when that first derivative is equal to 0. So let's go solve that. It's a quadratic. We end up with, there we are, a third or minus 1. Okay, let's test each of those. When x is negative 1, sub that into the second derivative. I get negative 4, which is less than 0. So negative 1, and I'm taking this opportunity to find the y value at the same time. So negative 1, 2 would turn out to be a maximum turning point. And if I sub in a third, I get positive 4. And therefore, well, the numbers aren't quite as nice as the other one, but a third, 22/27 is a maximum turning point. Now, by the way, that was a very easy function to differentiate. If you've got a hard function to differentiate, then you can still use the table of values. It might be quicker to do that rather than trying to find the second derivative. So, both tools are useful. Okay, let's talk a bit more about these inflection points, which is where the concavity changes. Just like we did with the first derivative. Remember what we were doing with the first derivative? We wanted to see what happens when the slope changes from positive to negative. Well, it's the same idea. So we're going to find the inflection points. Well, there's my first derivative. There's my second derivative. And the statement I write down for my working out is I say, and that first word's very important, possible points of inflection. They might not be inflection points. So the first step is to find possibilities. Then we'll go and test those possibilities. So 24x plus 12 is equal to 0. We've only got one possibility here. X is negative a half. All right, which kind of makes sense, I suppose. We are talking about a cubic. Let's draw up our table of values, but this time I'm looking at concavity rather than the slope. So minus a half, I know there's no concavity at minus a half, so I'll just draw a flat line for that one. So I've got to pick a point on the left-hand side, pick a point on the right-hand side. Once again, I can't go past any of the other possible points. Well, in this case, that's not an issue because I don't have any other possible points. The other thing I can't go past are any discontinuities. But again, there's no discontinuities in this curve, so I can pick any point I like. So the left-hand side of minus a half, yeah, it seems logical. I picked minus 1. So when I do my table of values, I write the number that I'm testing there. Okay, it's negative 1, and then I write the result. It's negative 12. Don't just draw the pictures. It's negative, so I know it's concave down. On the right-hand side, I picked 0 to test. Sub that in, I got positive 12, and so I have a happy curve. So I'm going sad, then happy, it changed. That's an inflection point. Here's another key thing to write down in your working out. Therefore, I know there is a change in concavity. That means it's a point of inflection. There is a special point of inflection, our horizontal point of inflection. Now, like we have on the classic cubic there, that's where not only is it an inflection point, but it's a stationary point as well. So in other words, the first derivative would be 0 because it's a stationary point. The second derivative would be equal to 0 because it is a possible point of inflection. And here's the one. You ready? You ready? And the third derivative would not equal 0. Third derivative? What the heck is he talking about? Right, the third derivative. If you think about it logically, look at the definition we just wrote down for a point of inflection, where there is a change in concavity. Wouldn't it be great if we had some mathematical tool that measured change? Hang on, we do. It's called the derivative. Just like the second derivative measures the change in the first derivative, logically, the third derivative must measure the change in the second derivative. So as long as the third derivative does not equal 0, so it has a value, there must be a change. The only thing that's saying there's no change is if it's equal to 0. We're saying third derivative equals 0, oh, there is no change. So as long as that number comes out to be non-zero, we know there's a change. So let's talk about that in more detail because it's actually a little bit more complicated than simply the third derivative is not equal 0. Possible points of inflections, that's going to occur, as I say, when the second derivative equals 0. Okay, if the first non-zero derivative, so you keep differentiating, and if the first time you substitute in and the derivative turns out to be 0 is of odd order, third derivative, fifth derivative, seventh derivative, ninth derivative, however long it takes, then that's a point of inflection. If it's an even order, then it's not a point of inflection. So had we done that and the third derivative turned out to be 0, but then subbed into the fourth derivative and it wasn't 0, then that's telling me it's not a point of inflection. So that's actually the test. As I say, it would be extremely rare for you to get an example where we'd have to go further than the third derivative on it. Well, I suppose I can explain because have a look at the cubic, okay? Y equals x cubed. What's the first derivative? Very good. What's the second derivative? 6. Okay, now that's at 0. That's 0. We've got a possible point of inflection. What's the third derivative? Oh, that's not 0. We have a change in concavity, okay? Because the first time it became 0 was at the odd derivative, or third derivative. Now, that's y equals x squared. I won't use that one. Pretend it's y equals x to the power of 4. I mean, we know what that looks like. Okay, what's the first derivative? 4x. Okay, second derivative? 12x squared. So, all right, we have a possible point of inflection at 0. What's the third derivative? 24. Substituting 0, we get? Keep going. What's the fourth derivative? 24. So the first time it's not 0 is the fourth derivative, therefore it's not a point of inflection, because that's an even one. And you can keep going. I mean, if you did x to the power of 5, the first time it would be non-zero, it would be at the fifth derivative, and so on and so on. Geometrically, why? Because what you're doing is finding double roots, triple roots. So if it's an odd order, imagine we were just curve sketching, and I said draw something and there was a factor there that was to the power of 5. Then at the x-axis, it would inflect through. That's what you would draw. So it's an inflection. So all that's really happening with this is that's what we're finding. It's just that we might have shifted the curve a bit. But effectively, it's exactly the same idea, and that's why it's working. If I was using this technique then, so back to our example we did before. So yes, remember I found the first derivative and the second derivative. Because they're asking me about inflection points, I would go and find the third derivative. And for our example, that's 24. So when I went and found the possible points of inflection, we came up with minus a half. Well, at minus a half, the third derivative is 24. It's always 24 for this particular curve. Well, that does not equal 0. Again, explain yourself. I'm saying there's no change because I've got a value for the third derivative. So therefore, there is a change in concavity. So minus a half 3 is a point of inflection.